So we can see if I'm moving around in the image frame here, all of these points here or all of these green lines will actually like follow my face. Hey guys, and welcome to a new video in this computer vision tutorial. In this video here, we're going to talk about optical flow. So we're going to talk about how we can use optical flow to detect like motion in our image. So how our environment or like our frame is changing between the camera and the actual like frame. So we can use it for tracking different kind of objects around in the frame. We can like track different kind of like specific objects or like dense optical flow. So we actually like just track everything and all the motion that is going on in the image. But in this video here, we're just going to mainly focus on finding some good features that we can track in the image, and then we're going to track those points over time in our image, and then we're creating this sparse optical flow. Then in another video, we're going to create dense optical flow, so we actually like look at the whole image and how the scene is changing over time in that image, and then we can use that to detect or like track objects in the whole frame that is changing like frame by frame. But first of all, we're going to join the Discord server. I'll link to it down in the description here. You can join the channel, share outs about computer vision, deep learning, AI, and so on. You can also become a member of the channel if you want to support the channel with a small monthly fee, and everything will go to create more and better quality content here on the channel. So thank you guys. So if we just start here in the OpenCV documentation, then we can go into these different kind of modules, and then inside the video analysis tool here, or like the module that we're going to use in this video here, we can go into this tab, and then we can go into object tracking. So we're actually going to track different kind of objects around in the image frame at specific points by using this optical flow. But we can go into object tracking, and then we can see all different kind of classes, functions, and so on that is implemented. And in this video here, we're going to focus on actually like creating this sparse pure L-key optical flow. So this is just like the algorithm that is implemented. We can also use, for example, like Kalman filters, dense optical flow, which we're going to talk about in another video, and so on. But in this video here, we're mainly going to focus on this sparse optical flow. So we're tracking around specific points that we're detecting. And then down here at the functions, we can actually like see all the different kind of functions that is implemented that we can use. So in this video here, we're going to use this calc optical flow pure LK. So this is this Lucas-Canade algorithm that is implemented. So here we can see that it calculates an optical flow for a sparse feature set using the iterative Lucas-Canade method with pyramids. So what we're talking about here is that we are detecting these different kind of like sparse feature sets by tracking good features in our image, and then we're creating this sparse optical flow with it. So we're actually like tracking around, and we're finding the trajectory of those points that we're detecting in the image. So we're actually like tracking objects instead of only detecting objects in this video here. So this can be used for a lot of different kind of things in real life applications. If you're looking at cars driving at a highway and you want to track like the trajectory of that car within our camera frame and so on. So this is actually like really nice, and it can be used for a lot of different kind of things. And it doesn't really take up that much computational cost. We can even run like the algorithms really fast, and we're also going to talk about how we can set up here on the GPU so we can run it even faster for real-time applications. But first of all here, I want to show you like what we can actually what the parameters are to this function. Then we're going into the code. We're going through line by line in the code, what it does and how we can set it up. And then we're going to use this function to actually like create this or like calculate here the optical flow for the features that we're tracking. And then we're going to see this results at the end. So first of all here, it takes an input array here and two inputs array here, like three input array. And then first of all, it takes the previous image. So down here, we can see the different kind of parameters. So the first parameter it takes is the previous image from this video stream. So here we have a first 8-bit input image or pyramid constructed by built optical flow pyramid. And then we take the next image in our image sequence. So this will be the second input image or the pyramid of the same size and the same type as the previous image that we passed through it. So again, we need to make sure that we have the same data types and so on when we're passing our images through this function. Then we have the previous point, so the vector here of the 2D points for which the flow needs to be found. So we have these point coordinates must be single precision floating point numbers. So these are actually just the points for the trajectory over time. So when we're actually like going to have our trajectories, these will just be our previous points and our next points here. So our next point here would actually be the output of this function. So we output a vector of 2D points with single precision floating point coordinates containing the calculated new positions of input features in the second image. So we load in our new image here, or like our next image, and then we're going to calculate the new positions of that optical flow or the trajectory of the points that we actually have by using the previous points here as well. So we actually like create this trajectory of our object that we're tracking around in the image frame. Then down here we will also get like some status here. We get some output here vectors here of the errors. We need to specify some parameters with the window size, so the search window at each pyramid level. So we already know like the window size is how many pixels are we actually like looking at the same time when we have this window passing through our image frame. We also have some max level here, criteria, and some optional frags that we can set down here that I'm going to show you when we set it up in the code. We can also have some min-ith threshold down here as well, but we're mainly going to focus on like what this function here takes as input and what it outputs, and then we can go into more details with this algorithm or like what is going on under the hood later on. So here the function implements a sparse iterative version of the Lucas-Canetti optical flow parameters, and we can just see that this is how we use it. We're going to go into the code and do it. So now we're jumped into Visual Studio Code here, and I'm going to go over line by line how we can set up this optical flow and what we need to make sure that we actually have the directory of the points or the objects that we're tracking around in the image frame with our optical flow. So first of all, we need to import our modules, and we need to set up some different kind of parameters for our algorithm and also some feature parameters when we're actually like detecting and tracking around our features in the image. The code here will be available on my GitHub. I'll link to it down in the description here, and you can just go into my GitHub, find the code, copy paste it, and run it on your own computer and just play around with some of these parameters here and just to see like how it works by yourself too. But here we have the algorithm parameters. So we know that we need to set up a window size. So we have 15 by 15. Which is our window size, and we also have this max level here and some criteria that we can set up for this LK algorithm here to actually like calculate the sparse optical flow. Then we also have some feature parameters, so we're going to track different kind of corners in the image where we want to specify like how many corners do we actually like want to track and what is the quality level of our corners. So if our corners is not above this quality level, we'll just discard them and we will only use the corners that is over this quality level here. So what this means is that we're only tracking the good features or the good corners in our image, and then we're going to actually create optical flow or like sparse optical flow with those points so we can track around those points in the image frame. So we also have a minimum distance here between the corners that we want to detect, and also the block size here, which is just 7 in this example when we actually like detecting our corners. So now we also have some parameters here that we need to set up for our trajectory length, and we also need to set up a detect interval. But up here we have 20 set as default for our trajectory length, which just means that we will have 20 points in each of the trajectories that we're going to have for each of our points. We can play around with it. If you don't want to track the object for so long, you can lower this parameter, or if you want to track it around the frame all the time, you will need to increase this parameter here as well, and don't delete it later on if you just want to get like the whole trajectory of the object or point that you're tracking around in the image frame. So the detection interval here is like how often do we want to actually like update our corners that we want to use to actually like create this sparse feature set that we showed in the documentation. So this parameter or like this function from OpenCV that we're going to use for optical flow, it takes in these this set of feature points, which will be the corners that we've extracted from this algorithm here. So our detection interval, if you increase this value here, it will be slower, so we will update our corners and our tracking slower. But if we have a detection interval here of 1, it will just update it every time we run through our algorithm. So we're going to have a list here with all of our trajectories. So in this list, all the trajectories that of the points that we're going to track around in the image frame will be stored in this list. And then we're just going to keep track of our frame index here in case that we want to change the detection interval later on. We're going to open up our webcam so we can just read in our images from the webcam. So while through here, so while we can read in images from a webcam, we're just going to be in this while loop. If we hit escape or Q at any time in our program, it will terminate, it will release the webcam, and it will destroy all the windows that we have opened up with OpenCV and ImShow. So first of all, here we need to set up our timer so we can see how many frames per second do we actually like get by creating these sparse optical flow. So we're just going to set up a timer, then we're going to calculate it later on and display it on our image. So that is not really that important, just to see how many frames per second do we get. So we're going to read on our frame here from our actual webcam, and then we're going to store the frame in this variable. We're going to convert the color here from BGR to grayscale because we know that when we pass our images through our function, we saw in the documentation that it takes an 8-bit input image with only one channel. Then we're just going to take our image here, which will be a copy of our frame. So we're just going to copy this frame here, and then we also have our grayscale frame. So now we're going to calculate the optical flow for sparse feature set using the iterative method here. So at the bottom here, we're going to create an actual feature set, but this is how we can calculate the optical flow. So if the length of our trajectories, so if there's any trajectories that we have tracked or like any objects that we're tracking around in the image frame, then we go into this if statement here, and we're going to use this calc optical flow pure LK. So first of all, here we're just going to set our M0 here and M1 here to the previous frame and the new frame that we get in now, and we're operating with grayscale images as we just talked about. So here will be the actual like points here that it returns. So know that this will be the point that it returns, and this will also be the points. But here we pass in the different kind of like parameters. So first of all, here we need to pass in the latest trajectory, so the last trajectory as this point here to the first image. So this will be the first point, and then our second point here will just be P1, which is the result that we get from this one. So this is just how we can get like points by points when we're actually like creating our trajectories and so on. So down here we are actually just going to pass in this method. First of all, we're converting our point here to a float to a 32-bit floating point number. Then we go through all the trajectories here, or we just take like the last trajectory that we have actually like stored. We're going to reshape it so we get this point that we can pass into this function. We get this point here, then return a new point of the actual optical flow, so how the motion changes from the frame to the other frame, because here we have our M0 and our M1, and this will be our previous frame and our new frame that we load in with the camera and grayscale. So then we're actually like just going to take the difference here between our two points here that we got back from this function. Then we're just going to reshape it and take the maximum value here of the last index. Then we can set up a threshold here. So if our difference here is less than 1, then we say that this is actually like a good optical flow that we've created with these points up here in our trajectories. And then we're actually like tracking our object or our corners around in the image frame good enough. And then we can use that later on to tell if we should actually like consider that as a trajectory or not. So now we're going to have a list here with new trajectories that we're going to have. So here we're going to get all trajectories. So first of all, we're going to have a for loop that is running through all the trajectories that we have. We're going to take the xy point of the trajectories, or like of these values that we just created up here with this P1. So this will just be a zip here of the trajectories, and our P1, which will be this point that we created up here with the optical flow. And then we just take the last parameter here, if it was actually like a good detection, or if the optical flow is actually like good because the difference between these two up here is low. So here we're going to check if our not good flag here is set. If our trajectory is not good enough, we will just continue. It will go out of the for loop. But if it's good enough, we can actually just append this point here to our trajectory. So we just keep updating our trajectories over and over again when we're actually like detecting our corners. So we're tracking around the corners in the image frame, and then we're just appending new points to it that we calculated with this calc optical flow function up here. So these are just the new points that we're updating, and then we can just have the trajectories by storing those points. And then down here, we can just check if the length of a trajectory is greater than our trajectory length, then we just delete the 0th element. So we just keep updating our list. So this will actually like just be running 10 values, or like running trajectory length of our tracking. So in this example here, we have 20. So we'll have 20 points in our list with our trajectory. And then if we exceed, or like when we get a new point in, the 21st point into our list, then we'll just delete the 0th element. So again, we will only have 20 points. So just keep updating it when our points, or like when our objects is moving around in the image frame. Then we're going to append this new trajectory that we have to our new trajectories, because then we have updated our trajectory and we can then store it in the new trajectories. We just draw a circle of the nearest detected point, so we can actually like always see where the nearest point is that we're detecting and tracking in the image frame before we're detecting a new one. And then this point will actually like be an older one, and we will give that another color, because then the motion has actually like changed in the image frame, and we will get in a new corner or like a new circle that we're detecting, appending that to our trajectories if it's good enough, and then we just keep updating our trajectories list. So this means that we need to set this new trajectories here equal to our trajectories. So we're just going to have our trajectories down here instead. So we're going to have our trajectories equal to our new trajectories, and then we can just draw all the trajectories here with this Polylines function from OpenCV. So we're going to have our image, then we're just going to run through all the trajectories. We make sure that this is a 32-bit integer value. So our trajectory here, and we just have a for loop running through all the trajectories and drawing those as polylines on our image. Then we're just going to put out some text like the track count, so how many points are actually like tracking around in the image frame with Optical Flow. Down here, we're going to update our interval, and then like when to update and detect new features. So this is the detect interval parameter that we can set up at the top. So in this example, it is just 1. So when we have our frame index modulus with detected interval, which is 1, it would always equal to 0 every time we run through this while loop, which means that we just keep updating our features that we want to detect as fast as possible. So here we're just going to take the latest point in our trajectory, so we can actually like display that on a mask, and then we can use that mask to actually like detect our corners when we're updating our features that we want to track. So here we just have our for loop running through our x, y values in our latest trajectory. So we're just going to take the latest trajectory in our trajectories, and then we will get an x, y coordinate for that point. And then we're just going to track to actually like put that point on our mask, that we can then see what is going on. We can see what points are we actually like tracking, what corners are we tracking around in the image frame with this mask. And this mask we will also use to track the good features, or like find the good features that we can then track with Optical Flow. So down here is the last part of this program here before we're going to see the results. So we can now detect the good features that we want to track around in the image frame. So these will be the corners. So we're just going to have this P here, which is our features that we're going to track. We're going to use good features to track here from OpenCV. We're going to pass in the grayscale image frame, and then we're going to set the mask equal to this mask that we just created up here at the top. So this will be the latest point in our trajectory that we actually like want to track around in the image frame. We need to pass in our feature parameters that we specified up at the top. So here we can see that we have our feature parameters. So we want to detect a maximum number of corners of 20, quality level above 0.3, minimum distance between the corners 10, block size 7. So these are just the parameters. You can play around with all the parameters in your own program, copy paste the code, run them, play around the parameters and see what happens, and just see the nice results that we're going to see in a second. So if we have some good features that we can track around in the image frame, then we're actually going to add that to our trajectories. So again, we're just updating our trajectories all the time. So every time we get in a new point that we actually like determined to be good enough, then we're just updating our trajectories all the time, having this running trajectory, tracking around the points or objects in our image frame with Optical Flow. So here we're just going to take the good features, the x, y value for good features that we actually like have, and then we're just going to append that x and y, or like that point that we have tracked, to our trajectories. So this will be the nearest point in our trajectories. Then we just keep repeating the process over and over again, and just updating these trajectory lists, or like this trajectories list that we have. We're just going to update the frame index here, so we'll just keep increasing in case that we want to decrease the update interval. We set the previous frame here equal to the new frame, or like the frame that we just loaded in from our camera, because then we'll use that information to generate the next trajectory, or like how the points are actually like changing from frame to frame, because this is what we're looking at when we're talking about Optical Flow in computer vision. So then we're going to end the timer, and we're going to calculate the number of frames per second that we get. And then we're just going to show the results. We will print out the frames per second on the image. We're going to show the optical flow with the tracking around with the corners that we detected up here. And then we're just going to show the mask here as well, so we can see what is going on and what are we actually like detecting our features on, and also the update rate of those features that we're tracking. If we hit Q, we'll just terminate our program. So here we're now going to run the program, and it will just open up everything, load the program, and we can now see here that we get this up here to the left. We can see over here to the right, we get this mask with all these points. So these are all the points that we want to track around in the image frame. We can see we get all these points here. So these are the best features or the best corners that we can track around in the image frame. And over here to the left, we can see these points and how they actually like change. So we can see the red point here is the nearest point from frame to frame. And then we have these green lines following our red dots here, which are our trajectories. So every time we have a green line, it is actually like a trajectory with 20 points in it. So we can see if I'm moving around in the image frame here, all of these points here, or all of these green lines will actually like follow my face with up to 20 points. And when I'm moving around, we will just keep updating it. So we only store 20 points at a time. So it's actually like really nice, really cool. And we can see that it actually like tracks around these different kind of things in the image frame. We can try to play around with some of the parameters here. We can maybe set up the trajectory length. So maybe if we set it to 40 here, and we can try to set the detection interval to 5. So we're not updating our points as fast, and then we're storing more points in our trajectory lists. So now we're just going to run the program here again and see what it does when we're changing these parameters. So here we can see that the update rate is way slower over here to the right of the features that we're going to track. And over here to the left, we can see that these green lines is actually like becoming longer and longer when we are moving around in the image frame. So we can use this for example, like just imagine a car, or you have a camera looking at a highway and you want to like track the trajectories of the cars driving on that highway. Then we can actually use optical flow for that, because we will just get all the points that we're actually like having in our image frame. So we're looking at how the motion is changing in the image frame with optical flow. We can even see up here that the track count is up to 70. So we're tracking around 70 points here in our image, sometimes down to 50, and we get like around 70-80 frames per second. So, and this is even only on a CPU. So we can run it in real time. We can use it for a lot of different kind of applications. It's just really nice to track around features and different kind of points. And in the upcoming videos, we're going to look at dense optical flow, so how we can look at the whole image frame and see how motion is changing in the whole image frame at the same time, instead of only looking at individual points, or like in this case up to 50 points in our image that we're tracking around. So thank you guys for watching this video here, and remember to hit the subscribe button and bell notification under the video, and also like this video here if you like the content and you want more in the future, because this is just really nice and it can be used for a lot of different kind of computer vision applications and so on. I have the computer vision tutorial where we talk about basic stuff about computer vision, like so image operations, camera calibration, stereo vision, and now we're talking about optical flow, tracking around different kind of objects. So if you're interested in that tutorial, I'll link to it up here, or else I'll see you next tutorial, guys. Bye for now.